Previously, we focused on understanding the meaning behind the Michaelis-Menten equation, and what we said was that the rate or the velocity at which the enzyme operates V0 is equal to the product of the maximum velocity, the maximum rate of the enzyme Vmax, and this ratio. So the numerator is the substrate concentration and the denominator is Km plus the substrate concentration. Now, previously we said that Km is known as the Michaelis constant, and we also said that the Michaelis constant has units of molarity. So the units of Km is the same as the units of the substrate concentration. In fact, inside our body, all the different enzymes have a Km value that range from about 0.1 molar to about 10 to the negative 7 molar. So we see that the Km value, the magnitude of the Km value depends not only on the type of enzyme and the type of substrate, but it also depends on the conditions in the environment. So by changing, for example, the pH or the temperature of the environment, we can affect the value of Km. Now, what exactly is the meaning behind Km? What is the physiological importance of the Michaelis constant? This is what we want to focus on in this lecture. And actually, previously, we discussed one meaning of the Michaelis constant, but as we'll see in this lecture, there are two ways that we can actually interpret the meaning of the Michaelis constant value. So let's begin with what we said in the previous lecture. So previously, in our discussion of the Michaelis constant, we said that the Michaelis constant represents the concentration of the substrate at which the enzyme's activity, the enzyme's rate, is exactly half of its maximum rate. So the Km describes the substrate concentration that is needed to reach exactly half of that maximum velocity of that particular enzyme. And what that basically means is when our substrate concentration is equal to Km, exactly half of all the active sites in the enzyme mixture are filled with the substrate. And this can be seen in the following diagram. So initially we begin with, let's say, an enzyme mixture that consists of 4 identical enzymes, and these are shown in red. And notice that each one of these enzymes contains this crevice, and that's the active site to which a substrate can actually bind. Now, if we take this enzyme mixture and we add a concentration of substrate that is equal to Km, the Michaelis constant, exactly half of these active sites will be filled. So in this case, if we add 2 of these blue molecules, then that means 2 of these enzymes will form the enzyme substrate complex as shown in this diagram. And so this means that exactly half of the active sites will be filled. And another way of saying this is in the following manner. So when the concentration of substrate is equal to Km, the concentration of the enzyme substrate complex, so ES, is equal to exactly half of the total initial concentration of that enzyme. So what that means is initially we began with 4 enzyme molecules, and when we add Km, namely the 2 blue molecules, then the concentration of the enzyme substrate complex will be equal to exactly half of that initial. So 4 divided by 2, and that gives us 2. And that's what we mean by this equation here. Now, not only that, but what that also means is the rate of activity, the velocity of that enzyme will be exactly half of the maximum. And that makes sense because if half the enzymes have active sites which are occupied, that means the rate will be exactly half of its maximum. So this is the first and perhaps the more important meaning of the Michaelis constant value. Now, what about the second meaning of the Michaelis constant? Well, this is where we have to actually recall some information that we discussed when we derived the Michaelis-Menten equation. So in our derivation on the Michaelis-Menten equation, we basically use the following chemical equation. And this chemical equation describes describes when that reaction, the enzyme catalyzed reaction, is in its beginning stages. So when the time is approximately equal to 0. And what this equation basically tells us is, if we take the enzyme, so this is the red enzyme, and we add the substrate, so given in blue, then what will begin to happen is some of the substrate will begin to bind onto the active site to form the enzyme substrate complex. And this is our intermediate. Now, what we also said was we assumed the steady state condition. And the steady state condition means that the concentration of this intermediate, the enzyme substrate complex, is not changing over time. So the concentration of this remains the same, even though this concentration and this can actually change over time. And by making that steady state assumption, we were able to basically create the following Michaelis constant. So Km, we said, was equal to K minus 1 plus K2 divided by K1, where K minus 1 is simply the rate constant for this reaction, the dissociation of the enzyme substrate complex back into the enzyme and the substrate. So when the substrate essentially dissociates from the active site, we produce back this enzyme and a substrate. That's K minus 1. K1 is basically the association, the formation of this enzyme substrate complex. And K2 is the rate constant for this reaction, the dissociation of the enzyme substrate complex into the product molecule and that enzyme. So we were able to basically derive this equation in that lecture. And we're going to use this equation in just a moment to basically give the Michaelis constant a second physiological meaning. So let's suppose, so this is the important assumption we want to make. Let's suppose that the dissociation of the enzyme substrate complex is much more rapid. So the dissociation of the enzyme substrate complex into the enzyme and a substrate. So the reaction going this way takes place much more quickly than the reaction going this way. So the dissociation going this way takes place much more readily than our dissociation into the enzyme and this product. So we suppose that the enzyme substrate complex dissociates into E and S much more rapidly and much more readily than E into P. And what this basically implies is the value of K2 is much smaller than the value of K minus 1. Because if this rate is much greater, that implies that K minus 1 must be much greater than K2. And if K minus 1 is assumed to be much larger than K2, we can simplify this equation in the following way. So the Michaelis constant Km is equal to, so K minus 1 plus K2 divided by K1, and because K minus 1, this quantity, is much greater than K2, for example, let's say if this is 1 million and this is 1, then 1 million plus 1 doesn't really change the value of K minus 1 by too much. And so what that means is we can approximate this to equal to this. So because this is much smaller than this sum is approximately equal to simply K minus 1. So our numerator is replaced by K minus 1. And so we see that the Michaelis constant is approximately equal to K minus 1 divided by K, assuming that K2 is much smaller than K minus 1. And this is where we give meaning to the Michaelis constant. What this basically means is the Km value, the Michaelis constant, describes the equilibrium dissociation constant of the dissociation of the enzyme substrate complex back into the enzyme and the substrate. So in such a case, Km describes the equilibrium constant of the enzyme substrate complex dissociation. And to see why that's so, let's take a look at this equation. So we basically take this equation and we flip it going this way, and we obtain this. So the enzyme substrate complex dissociates back into the enzyme and a substrate, and the rate constant going this way is given to be K minus 1. Now going backwards, the enzyme and the substrate reassociate to form back the complex. So this is the rate constant going this way, this is the rate constant going in reverse. Now, if we assume this takes place very quickly, then equilibrium is established very quickly. And if equilibrium is established, what that means is the rate of the forward reaction is equal to the rate of the reverse reaction. And so we can basically determine what the rate law is of this reaction and the reverse reaction, and we set them equal. So the rate law going this way is given to us by K minus 1 multiplied by the concentration of, this should be the enzyme substrate complex. And that is equal to going this way, so K1 multiplied by the concentration of the enzyme and the concentration of the substrate. So this we obtained by assuming that this was at equilibrium. And that's a good assumption because this reaction takes place very quickly. Now we could basically solve for K minus 1 divided by K. So we basically take this, we bring it to this side, take this, bring it to this side, and we get this proportion. So K minus 1 divided by K is equal to the product of these two concentrations divided by the enzyme substrate concentration. And this, from general chemistry, we define to be the equilibrium constant of the dissociation of the enzyme substrate complex. And because Km is equal to K minus 1 divided by K, which is the same thing as here, the equilibrium constant is equal to Km. So we conclude that the second meaning of the Michaelis constant, as long as we make the assumption that K minus 1 is much greater than K2, so this reaction is much quicker than this reaction, we basically see that the Michaelis constant describes the likelihood of the dissociation of the substrate from the active site of that enzyme. So we see that if the Km value is very large, then that means our numerator term in the ratio is much greater than our denominator term. And if the numerator term is large compared to our denominator, that means we have a high concentration of the enzyme and the substrate in its dissociated form. And that implies that the substrate does not bind very strongly to the active site of that enzyme. So we see that if Km is large, the enzyme binds weakly to the substrate, and there is a high probability that the substrate will dissociate from the active site of the enzyme because Km describes the equilibrium constant. On the other hand, if Km is actually small, then that means we have a small concentration of the enzyme and the substrate in its individual form compared to the complex form. And so if the Km is small, equilibrium will lie to the left side, so we'll have a lot of the enzyme substrate complex, and that means the substrate will bind strongly and tightly to the active site of the enzyme. So if Km is small, the enzyme binds tightly to the substrate, and the substrate will tend to remain bound to the active site. So we see that we can actually give two different meanings to the Michaelis constant. So physiological meaning number one is the Km describes the concentration of that substrate when the enzyme's activity, the velocity of the enzyme, is exactly half of the maximum velocity, and at this point exactly half of the active sites on the enzyme mixture are actually filled with the substrate. Now, and this must be emphasized, we can only use this second meaning as long as we remember that we made this assumption, because this entire work is only meaningful if this is actually used. So if this is true, if K1 is much greater than K2, and what that means is if the dissociation of the enzyme complex going this way takes place at a much higher rate than the enzyme substrate complex dissociation going this way, then in that particular case, the Michaelis constant also describes the likelihood that the substrate will dissociate from the enzyme. If Km is high, that means our dissociation constant is high, and so our equation will shift towards the right side, and that means our complex will be very likely to actually dissociate into these products. But if the Km is very small, then that means it binds very tightly, the substrate binds tightly into the active side of that enzyme, and so the equilibrium will shift this way. So once again, Km describes the likelihood that the substrate will dissociate from the enzyme. If Km is high, it will be likely to dissociate. If the Km is low, it will not be very likely to actually dissociate into that enzyme and that individual substrate.